Welcome viewers to the third lecture for the online series of lectures for the course of Algebraic Topology 1. In the previous lecture, we have seen that any convex subspace of the Euclidean space R to the n has trivial fundamental group. We now need to know how to compute fundamental groups of topological spaces that are non-trivial. One useful technique for achieving this is to use the tool of covering spaces. Therefore, our third lecture is dedicated to this very important tool of covering spaces. Let us get to the definition. Let P from E to B be a continuous surjective map the open set U of B is said to be evenly covered by the map P if the inverse image P inverse U can be written as the union of these joint open sets V alpha in E such that for each alpha the restriction of P to V alpha is a homeomorphism of V alpha onto U. The collection V alpha, alpha running in an index set, will be called a partition of P inverse U into slices. Okay, so let me draw a picture to illustrate this fact. We have an open set here called U in B. So here is the map P from E to B. This is the open set U in B, and here is the pre-image of U. Okay. And the pre-image of U is like a union of copies of U. Okay. So this is P inverse U can be written as disjoint union of open sets V alpha. So each V alpha is open in the topological space E. Okay, so P projects these slices to the open set U. So the caption of the figure is even covering of U being a subset of B by the map P from E to B. Okay, good. Now the definition of covering map. Let P from E to B be continuous and surjective as before. If every point B in the topological space B has a neighborhood U that is evenly covered by the map, then P is called a covering map, and E is said to be a covering space of B. Okay. So these are the definitions of covering map and covering space of the topological space B. Okay. So now there are a few properties of this covering map that actually follow from the definition of it. Okay. Let us discuss these properties in detail. The first property is that if P from E to B is a covering map, okay, then for each B in the topological space B, the subspace P inverse B, which is equipped with the topology, which is equipped with the subspace topology inherited from E, with the subspace topology inherited from E, happens to have the discrete topology. It means that the subspace topology on P inverse B coincides with the discrete topology on it. Okay, so let us see how it happens. Let me erase everything. It actually follows from the fact that P inverse B intersected with V alpha is a singleton for each alpha in J. Okay, let us prove it by contradiction, which means that we assume the contrary. If there were more than one element in this set, P inverse B intersected with V alpha, then one would have had okay if there were more than one element in this set, for a given alpha in the index set J, say C and D in this set, then one would have had for both C and D in V alpha, since C and D are in the intersection, C and D are also in V alpha. P of C to be equal to P of D to be equal to B. Okay, it follows from the definition of the inverse image of a point. Okay, resulting in the fact that P restricted to V alpha from V alpha to U is no longer injective. Okay, which means that two elements like C and D in V alpha, we have the same element B in U, meaning that P is not injective. And hence, this guy would not be a homeomorphism contradicting the fact that P is a covering map of B. Okay. And that is the reason this set is a singleton. It consists of a set containing one element only. It is a set with one element only. Okay. Also note that since B is an element of the open set U, the inverse image of B under P has to be contained in P inverse U, and P inverse U is a disjoint union of these open sets V alpha, right? So since P inverse B is contained in this set, the intersection of P inverse B with this disjoint union is going to be just P inverse B, right? Now, using elementary set theory, we can rewrite this as the disjoint union of the intersection of P inverse B with V alpha. And this guy, this disjoint union, is equal to P inverse B. Okay? Therefore, we conclude that each element of P inverse B is an element belonging to a one element set of the mutually disjoint family P inverse B intersected with V alpha, alpha running in the index family J. And each one element set of this family is an open set of P inverse B according to the definition of subspace topology. Okay. Since V alpha, each V alpha is open in E, and P inverse B considered as a subset of E, no, for that subset, P inverse B intersected with V alpha is going to be an open subset in P inverse B in subspace topology. Okay. So each one element set is an open subset of P inverse B. Okay. So any subset of P inverse B is an open subset and a closed subset at the same time. So P inverse B is actually endowed with the discrete topology, and that is the reason the subspace topology on P inverse B coincides with the discrete topology on it. Okay. So this is what we write now, that hence the subspace topology that P inverse B inherits from E is the discrete topology. That is, each subset of P inverse B is open and closed at the same time. Okay. That is, in other words, all subsets of P inverse B are both open and closed, which is the definition of discrete topology. Now the second fact, or the second property related to the covering map. Note also that if P from E to B is a covering map, then P is an open map. It means that if I pick up an open subset from E, the image of that open subset under P is going to be an open subset in B. Let us prove this fact. Let A be an open subset of E. We need to show that P of A is open in B. Okay, so let us draw a diagram here explaining the situation. We have this topological space B, and inside this topological space is an open set P of A, not an open set, if we don't know it's open. So there is a subset here in B. Okay, and we choose a point X in this subset. Okay, if PA is open in B, we will be able to find a neighborhood of X that is contained entirely in P of A. Okay, something like this. All right. So PA is open in B. That is what we need to prove. Let X belong to P of A, as in the diagram. We need to find an open subset of B. This dotted subset is an open subset of B containing X. It has to contain X, containing X, and which itself is contained inside P of A. This is P of A, and this subset has to be contained inside P of A. If we can show that such open subset of B exists, then we'll be able to show that P of A is open in B. Okay, so let us prove the existence of this open subset of B. Okay, so let me erase these things. Since P is a covering map of B, one can choose a neighborhood U of X that is evenly covered by B. That is evenly covered by P. Covered by P. Okay, so let us take that open subset to be like this. No, I think if we can take this to be something like this, and open subset this is U that is evenly covered by P, meaning that there are these slices, right? This is pre-image of U under P. Okay, so let V alpha in the index set J be a partition of P inverse U into slices, that is P inverse U is equal to disjoint union of V alphas. Okay, we can always do that since P is a covering map. Now since X is in P of A, okay, there exists an element Y in A such that X is equal to Py. It follows from the definition of P of A. Okay. Since X is equal to Py, we know that X is in U, right? This X is inside this open set U. One has Y belonging to P inverse U. Of course, P inverse U, according to the definition of a covering map, can be written as a disjoint union of these V alphas, right? Which means that Y belongs to one of the V alphas in this disjoint union. Let us take that V alpha to be V beta. Let V beta be the slice that contains Y. V beta is of course a subset of E, right? The topological space E. And by hypothesis, A is open in E. Okay. Therefore, in subspace topology, V beta intersected with A is open in V beta. Okay. This is in subspace topology. Okay. Now, since by the definition of covering map, V beta is mapped homeomorphically onto U So P maps V beta to U homeomorphically. From the definition of homeomorphism, any subset of V beta, any open subset of V beta under the map of P going to be an open subset of U. Okay? Hence, P of V beta intersected with A is open in U. Follows from the definition of homeomorphism. Okay? Now, since U is open in B and and P of B beta intersected with A is open in U. Okay, so since P of V beta intersected with A is open in U and U is open in B, it follows from the lemma 16.2 on page 89 of the same book by Moncres. That P of V beta intersected with A is open in B. Okay? So this guy is open in B. Good. Now, we know that Y is in V beta. We have seen it, right? And Y is also in A. Okay. Remember that we showed the existence of such an element Y in A such that Px is equal to Y, right? So Y is in A and Y is in V beta, so that Y is in the intersection. Hence, we see that P of Y is in P of V beta intersected with A. But like we said that, sorry, I think I mistook it. Y is equal to P of X, right? We showed that we showed that X is equal to P of Y. So there existed Y in A such that X is equal to P of Y, right? So X is equal to P of Y, and so which means that X belongs to P of V beta intersected with A. Okay, and obviously P intersected in P of V beta intersected with A is a subset of P of A, So therefore we've seen that for any x in PA being a subset of B, there exists P of V beta intersected with A open in this topological space B with X containing with X belonging to P of V beta intersected with A, and P of V beta intersected with A is contained in P of A. So this is the neighborhood that we were looking for, which contains X and which itself is contained in P of A. That establishes the fact that P of A is indeed open in B, in the topological space B. Therefore, P is an open map. Open map. QED. Okay. Good. Now we study an example of a covering space. The first example, which is a sort of trivial example. Let me give you this trivial example first. Let X be an arbitrary topological space. Topological space. And we form this product space E being the product of X with a finite set 1, 2 all the way up to big N. Okay. Well, X is a topological space, given topological space, and this set is equipped with discrete topology. So this is a topological space as well, and E is endowed with the product topology of these two topological spaces. So E is also a topological space. This is given. The topology here is the discrete topology. Discrete topology. Okay. Then the projection onto the first factor P from E to X by P of X comma Y being equal to X is a covering map. Okay. Good. So let's see how it is a covering map. Before that, I want to draw a picture of the situation. So let me do it. Let this be the topological space X. So I attach the label N to it, meaning that it's the nth copy of this topological space X in the product E. Okay. And let me draw the other copies. I have to center it so that they look the same. Okay. I need another. Sort of difficult to center it. It's not okay, I guess. Okay, so these are all copies of X. Okay, this is the first copy, this is the second copy, and that's the nth copy of X. Okay, alright, so let me draw a straight line now. Okay, alright, these are the n copies, and then I need the base space, right? The base space being also a copy of X. Something like this. Okay, this is also X, and this is the covering map P, which is the trivial cover given by this equation. Projection onto the first factor. Right. So note that the whole set X being open in X. Okay, so in the topological space X itself is open, right? From the definition of topology. And this open set is evenly covered by P. Okay, indeed, the preimage of X under P using this definition can be written as it is joint union of these open sets in this topological space E. Let's see. Okay, it's immediate using this definition, but how these sets are open here in this topological space, because X is open here in big X, and these singletons are open here, right, in discrete topology. So the product of these two open sets is open in E in the product topology. Okay, so each of these slices are open sets in E, and P restricted to each of these slices X cross the singleton I is a homeomorphism, is obviously a homeomorphism from X cross the singleton I to X. Okay, this is a homeomorphism. Okay, good. So this is the first example of a covering map. So the second example of a covering map that we'll discuss is that of a circle. Okay, so we are going to do it in the next segment. So we'll end the first segment here. Okay, thank you for attending the first segment.